Welcome to this video on the Digital Logic Trainer board. This board is designed as a practical learning platform for understanding digital electronics through hands-on experimentation. Instead of using a breadboard with loose components, this trainer board provides a structured and reliable environment for building and testing digital circuits. A wide range of commonly used logic-integrated circuits are available on the board, including basic gates, flip-flops, counters, decoders, multiplexers, and arithmetic circuits. All IC pins are conveniently routed to connector headers, allowing circuits to be created using simple hookup wires. Input protection and pull-up networks ensure stable logic levels, preventing floating inputs and unpredictable behavior. Visual indicators such as LED lights and display modules make it easy to observe logic states in real time. The board also includes built-in clock generation and pulse circuits for sequential logic experiments. Whether you are a student, hobbyist, or instructor, this trainer board simplifies digital circuit development and debugging. In this video, we will explore the design philosophy, major sections, and practical usage of the board. Let us begin. Schematic explanation. We will go through the circuit section by section. First, consider 74HC00 IC. 74HC00 is a quad 2-input NAND gate integrated circuit. This device contains 4 independent NAND gates inside a single package. Each NAND gate has 2 inputs and 1 output. For reliable digital operation, it is extremely important that no CMOS input is ever left floating. A floating input can randomly switch between logic high and logic low due to noise, interference, or leakage currents. This leads to unstable outputs and confusing experimental results, which is undesirable in a lab environment. To prevent this problem, the board uses 10 kΩ pull-up resistors. Each input line is connected to the 5-volt supply through a 10 kΩ resistor. This means that whenever a student does not connect anything to the input header, the input automatically assumes a logic high state. When the input pin is intentionally connected to ground using a jumper wire or switch, the input becomes logic low. Thus, the resistor establishes a well-defined default logic level. Using 10 kΩ resistors provides a good balance. They are strong enough to prevent noise sensitivity, yet weak enough to avoid excessive current when the input is pulled low. This approach ensures predictable and stable behavior of the logic gates during experiments. On the trainer board, all primary gate inputs, A1, B1, A2, B2, and so on, follow the same design philosophy. By standardizing the pull-up network, students can safely perform wiring experiments without worrying about undefined logic states. This simple but crucial design practice greatly improves the usability and reliability of the trainer board. In this portion of the schematic, we see a 74HC02 integrated circuit. The 74HC02 is a quad 2-input NOR gate device. It contains 4 independent NOR gates within a single package. As with all CMOS logic devices, the inputs must never be left floating. Floating inputs can cause unpredictable switching and unstable outputs. To ensure a defined logic state, each input line is connected to the 5-volt supply through a 10 kΩ pull-up resistor. In this section of the circuit, we have a 74HC04 integrated circuit. The 74HC04 is a hex inverter device. It contains 6 independent NOT gates within a single package. An inverter simply reverses the logic level of the input signal. A logic high at the input produces a logic low at the output, and vice versa. 10 kΩ pull-up resistors are provided to the inputs. In this section, we are looking at a 74HC08 integrated circuit. The 74HC08 is a quad 2-input and gate device. It contains 4 independent AND gates within a single package. An AND gate produces a logic high output only when both inputs are high. If either input is low, the output becomes low. To ensure stable operation, each input is connected to the 5-volt supply through a 10 kΩ pull-up resistor. In this section of the circuit, we have a 74HC32 integrated circuit. The 74HC32 is a quad 2-input OR gate device. It contains 4 independent OR gates within a single package. An OR gate produces a logic high output when either input is high. The output becomes low only when both inputs are low. To ensure stable logic levels, each input is connected to the 5-volt supply through a 10 kilo-ohm pull-up resistor. In this section, we are examining a 74HC74 integrated circuit. The 74HC74 is a dual D-type flip-flop device. It contains 2 independent flip-flops within a single package. Each flip-flop stores 1 bit of digital data and operates based on a clock signal. On the active clock edge, the logic level present at the D input is transferred to the Q output. The device also provides asynchronous control inputs, namely set and reset. These inputs can directly force the output state, independent of the clock. To ensure stable operation, all control and data inputs are connected to the 5-volt supply through 10 kilo-ohm pull-up resistors. In this section, we are looking at a 74HC86 integrated circuit. The 74HC86 is a quad 2-input exclusive OR gate device. It contains 4 independent XOR gates within a single package. An exclusive OR gate produces a logic high output when the 2 inputs are different. If both inputs are the same, either high or low, the output becomes low. To ensure reliable logic levels, each input is connected to the 5-volt supply through a 10 kilo-ohm pull-up resistor. In this section of the trainer board, we are looking at a 74HC107 integrated circuit. The 74HC107 is a dual JK flip-flop device. It contains 2 independent JK flip-flops within a single package. A JK flip-flop is a versatile sequential logic element. Depending on the logic levels applied to the J and K inputs, the output can hold its state, reset, set, or toggle. When both J and K are high, the flip-flop toggles its output on the active clock edge. This makes the device useful for counters and frequency division circuits. To guarantee stable operation, all inputs are connected to the 5-volt supply through 10 kilo-ohm pull-up resistors. In this section, we are examining a 74HC138 integrated circuit. The 74HC138 is a 3-to-8 line decoder and demultiplexer. It converts a 3-bit binary input into one of 8 active outputs. The inputs A0, A1, and A2 form the select lines. Based on their binary combination, exactly one output line becomes active. The device also includes enable inputs, labeled E1, E2, and E3. These control whether the decoder is active or disabled. When the enable conditions are satisfied, the selected output is driven low, while all other outputs remain high. This active-low behavior is a key characteristic of the device. To ensure stable logic levels, all input and enable pins are connected to the 5-volt supply through 10 kilo-ohm pull-up resistors. In this section of the circuit, we are looking at a 74HC151 integrated circuit. The 74HC151 is an 8-to-1 multiplexer. It selects one of 8 data inputs and routes it to a single output. The inputs labeled I0 through I7 are the data inputs. Only one of these inputs is passed to the output at any time. The selection is controlled by the 3 select lines, S0, S1, and S2. These lines form a 3-bit binary address that determines which input is chosen. The device also includes an enable input. When the enable is inactive, the multiplexer output is disabled regardless of the select lines. To ensure stable operation, all data, select, and enable inputs are connected to the 5-volt supply through 10 kilo-ohm pull-up resistors. The 74HC194 is a 4-bit bidirectional universal shift register. It can store and shift digital data in multiple ways. The register supports parallel data loading as well as left and right shifting operations. The mode of operation is controlled by the select inputs S0 and S1. Depending on the select signals, the register can hold its current state, shift left, shift right, or load new parallel data. The device also includes a clock input. On each active clock edge, the selected operation is performed. To ensure stable logic levels, all control and data inputs are connected to the 5-volt supply through 10 kΩ pull-up resistors. In this section of the circuit, we are looking at a 74HC2A3 integrated circuit. The 74HC2A3 is a 4-bit binary full adder. It performs the addition of two 4-bit binary numbers. The inputs labeled A0 through A3 form the first operand. The inputs labeled B0 through B3 form the second operand. The device also includes a carry-in input. This allows multiple adders to be cascaded for wider arithmetic operations. The outputs labeled sum 0 through sum 3 represent the result of the addition. A carry-out signal is generated if the sum exceeds the 4-bit range. To ensure stable logic levels, all input lines are connected to the 5-volt supply through 10 kΩ pull-up resistors. In this section, we are examining a 74HC390 integrated circuit. The 74HC390 is a dual decade counter device. It contains two independent counters within a single package. Each counter divides the input clock frequency and produces a sequence of binary outputs. These counters are commonly used for frequency division and counting applications. The device includes clock inputs and master reset inputs. The reset input forces the counter outputs back to 0 when activated. With every valid clock pulse, the counter advances its output state. This produces predictable digital counting sequences. To ensure stable logic levels, all control inputs are connected to the 5-volt supply through 10 kΩ pull-up resistors. The 74HC393 is a dual 4-bit binary counter. It contains two independent ripple counters within a single package. Each counter advances its output state in response to clock pulses. The outputs represent a binary counting sequence. These counters are widely used for frequency division and digital timing applications. Each stage divides the clock frequency by 2. The device includes clock inputs and reset inputs. Activating the reset forces the counter outputs back to 0. To ensure stable logic levels, the control inputs are connected to the 5-volt supply through 10 kΩ pull-up resistors. In this section, we are examining a 74HC4511 integrated circuit. The 74HC4511 is ABCD to 7-segment latch and decoder driver. It is designed to control a 7-segment display. The inputs represent a 4-bit binary coded decimal value. Based on this input, the device generates the appropriate segment control signals. The outputs labeled QA through QG drive the individual segments of the display. This allows numeric digits to be visually represented. The device includes control inputs such as lamp test, blanking, and latch enable. These inputs provide additional display control functions. To ensure stable logic levels, all input and control pins are connected to the 5-volt supply through 10 kΩ pull-up resistors. In this section, we are examining a 74HC10 integrated circuit. The 74HC10 is a triple 3-input NAND gate device. It contains 3 independent NAND gates, each with 3 inputs. A NAND gate produces a logic low output only when all inputs are high. For any other input combination, the output remains high. To ensure stable logic levels, each input is connected to the 5-volt supply through a 10 kΩ pull-up resistor. In this section, we are examining a 74HC27 integrated circuit. The 74HC27 is a triple 3-input NOR gate device. It contains 3 independent NOR gates, each having 3 inputs. A NOR gate produces a logic high output only when all inputs are low. If any input is high, the output becomes low. To ensure stable operation, each input is connected to the 5-volt supply through a 10 kΩ pull-up resistor. In this section, we are examining a 74HC11 integrated circuit. The 74HC11 is a triple 3-input AND gate device. It contains 3 independent AND gates, each with 3 inputs. An AND gate produces a logic high output only when all inputs are high. If any input is low, the output becomes low. To ensure stable logic levels, each input is connected to the 5-volt supply through a 10 kilo-ohm pull-up resistor. In this section, we are examining a 74HC4075 integrated circuit. The 74HC4075 is a triple 3-input OR gate device. It contains 3 independent OR gates, each having 3 inputs. An OR gate produces a logic high output when any one of its inputs is high. The output becomes low only when all inputs are low. To ensure stable logic levels, each input is connected to the 5-volt supply through a 10 kilo-ohm pull-up resistor. In this section, we are looking at the 7-segment display interface. The display used here is the HDSP5501 LED display module. Each segment of the display is driven through a 470 ohm resistor. These resistors act as current limiting components. Current limiting is essential for LED displays. Without these resistors, excessive current could damage the segments. The connector pins route the segment control signals from the logic circuitry to the display. Each signal corresponds to an individual segment, labeled a through G, along with the decimal point. By controlling these lines, different numeric digits can be displayed. This resistor network ensures safe and reliable operation of the LED display on the trainer board. In this section, we are looking at the LED indicator array of the trainer board. Multiple LED lights are connected to the connector headers through 1 kilo-ohm resistors. These resistors serve as current limiting components. They protect the LED lights by preventing excessive current flow. Each LED acts as a visual indicator for a digital signal. When the corresponding signal is high, the LED turns on. When the signal is low, the LED turns off. This arrangement allows students to directly observe logic states during experiments. Using LED lights as indicators greatly simplifies debugging and understanding of digital circuits. The resistor network ensures safe, reliable, and consistent LED operation across the board. In this section, we are looking at the NE555 timer circuit. The NE555 is configured as an adjustable multivibrator. In this mode, the device continuously generates a square wave output without any external triggering. The timing components, consisting of resistors and capacitors, determine the oscillation frequency. The threshold and trigger pins work together to control the internal charging and discharging cycle of the capacitor. As the capacitor voltage rises and falls, the output toggles between logic high and logic low. An LED is connected to the output through a current limiting resistor. This provides a visual indication of the oscillation. A series resistor is also included to safely route the output signal to the connector header. This circuit serves as an onboard clock source for digital experiments on the trainer board. In this section, the NE555 timer is configured as a monostable multivibrator. In monostable mode, the circuit generates a single output pulse in response to a trigger event. Under normal conditions, the output of the timer remains in a stable state. When a valid trigger signal is applied to the trigger pin, the internal circuitry is activated. This causes the output to switch state and start the timing cycle. The duration of the output pulse is determined by the external resistor and capacitor connected to the timer. During this interval, the capacitor charges through the timing resistor. Once the capacitor voltage reaches the threshold level, the timer resets automatically and the output returns to its original stable state. An LED is connected to the output through a current limiting resistor. This provides a visual indication of the generated pulse. A series resistor is also included to safely route the pulse signal to the connector header. This configuration is useful for generating precise single pulses for timing and control experiments. In this section, we are looking at the push-button switch interface of the trainer board. Each switch is connected to a 4-pin connector header. When the switch is pressed, the corresponding signal line is electrically connected, generating a logic transition. When the switch is released, the connection is removed, returning the signal to its default state. These switches allow users to manually generate digital input signals during experiments. They are commonly used for testing counters, flip-flops, and control logic circuits. By pressing the switches, students can observe real-time changes in circuit behavior. This simple interface provides a convenient method for human interaction with the digital system. In this section, we are looking at the power distribution headers of the trainer board. Two connector blocks are provided to distribute fixed logic levels across the board. One header is tied to the 5-volt supply through a 0-ohm resistor. This effectively acts as a direct connection to the positive supply rail. The second header is tied to ground, also through a 0-ohm resistor. This provides a convenient ground reference for experiments. 0-ohm resistors are commonly used as configurable links or PCB jumpers. They allow easy routing and optional modifications during assembly or debugging. These headers provide quick access to logic high and logic low levels. Students can use them for wiring inputs, testing circuits, and powering external modules. This arrangement improves flexibility and ease of use of the digital trainer board. In this section, we are looking at the USB power input stage of the trainer board. A USB Type-B connector is used to provide the 5-volt supply to the circuit. The 5-volt line from the USB connector is routed directly to the board's power rail. Ground from the USB connector is connected to the common system ground. A 10 microfarad capacitor is placed across the supply line. This capacitor provides bulk decoupling and helps stabilize the incoming voltage. It reduces noise and smooths any small fluctuations from the external adapter. To power the board, a standard regulated 5-volt USB adapter can be connected. This provides a convenient and widely available power source for the trainer board. In this view, we are looking at the top side of the digital logic trainer board. All integrated circuits are arranged in functional groups, such as NAND gates, NOR gates, inverters, AND gates or gates, flip-flops, counters, decoders, multiplexers, and adders. At the top of the board, Berg connector headers are provided for signal access. Each pin of every logic IC is routed to the connector system. Importantly, every IC pin is connected to 2 header pins. This dual-pin routing greatly improves usability during laboratory experiments. Students can insert hookup wires without mechanical stress or congestion at a single node. Multiple connections can be made to the same signal point when needed. Because all IC pins are exported to headers, any digital circuit can be constructed externally using simple jumper wires. This eliminates the need for a breadboard while retaining full wiring flexibility. The board therefore functions as a reusable hardware platform for experimenting with digital logic concepts. Power distribution headers provide easy access to logic high and logic low levels. Input conditioning networks ensure that unused CMOS inputs do not float, maintaining reliable circuit behavior. LED indicators and display sections allow immediate visual observation of logic states. Overall, this board provides a structured, robust, and flexible environment for learning, testing, and demonstrating digital electronics. In this view, we are looking at the bottom side of the digital logic trainer board. All integrated circuits are mounted on this side of the PCB. Placing the ICs on the bottom layer provides several practical advantages. First, it improves accessibility for soldering, inspection, and maintenance. If a device needs replacement, it can be desoldered and repaired more easily. This layout also protects the components during repeated laboratory usage. Each integrated circuit is provided with a dedicated decoupling capacitor. These capacitors are placed very close to the power pins of the ICs. Decoupling capacitors play a critical role in digital circuits. They suppress noise, stabilize the supply voltage, and reduce transient disturbances caused by switching currents. By positioning the capacitors near the ICs, the board minimizes supply loop inductance and improves noise immunity. This results in more reliable logic operation and fewer unexpected glitches. Overall, the bottom-side component placement improves serviceability, robustness, and electrical stability of the trainer board. This brings us to the conclusion of our overview of the digital logic trainer board. Throughout this video, we have explored the structure, design philosophy, and key functional sections of the board. The trainer board provides a stable and flexible platform for building and testing digital circuits without the complexity of traditional breadboarding. By routing every integrated circuit pin to accessible headers, the board allows virtually any logic experiment to be implemented using simple hookup wires. Pull-up networks ensure reliable logic levels, while decoupling capacitors maintain clean and stable power for the devices. Visual indicators such as LED lights and display modules make circuit behavior easy to observe and debug. Built-in clock and pulse generation circuits further simplify sequential logic experiments. Overall, this board serves as a powerful educational tool for learning, demonstration, and rapid prototyping of digital systems. Thank you for watching, and I hope this video helps you make the most of the Digital Logic Trainer board.